In the spring of 2012, the United States Senate Armed Services Committee published the results of an investigation that had taken more than 2 years to conduct. The investigation had examined the presence of counterfeit electronic components in the American defense supply chain. The investigators found more than 1 million suspected counterfeit parts in the supply chains of American defense contractors and subcontractors. The affected systems included the thermal weapon sights used by American soldiers, the APQ-180 terrain-following radar used by the B-1B Lancer bomber, displays used on military transport aircraft, and components in missile systems. The parts had largely originated in China and had entered the American defense supply chain through a network of independent distributors and brokers that had acquired the components with inadequate verification of their origin and authenticity. The parts are not obviously defective in all cases. Some were sophisticated enough to function in normal testing. The concern was not only the parts that failed, though some did, but the parts that passed basic testing but whose long-term reliability, failure mode characteristics, and performance under operational stress were unknown and potentially compromised. A counterfeit component that functions during a pre-mission test and fails during a mission is a different category of risk than a component that fails visibly during inspection. The industrial geography of counterfeit electronics is centered on Shenzhen, China, the city that also hosts the legitimate manufacturing operations of some of the world's largest electronics producers, and that constitutes the most sophisticated electronics manufacturing ecosystem in existence. The proximity is not coincidental. The counterfeiting industry in Shenzhen exists in a specific relationship with the legitimate industry. It draws on the same pool of manufacturing talent, the same supply of components and materials, and the same infrastructure of manufacturing equipment. Workers who have spent years on legitimate production lines understand the processes well enough to replicate them in facilities that are not subject to the quality control, intellectual property enforcement, or regulatory oversight of legitimate operations. The range of products produced ranges from obviously fake consumer goods, the counterfeit iPhones sold openly in electronics markets, which may function adequately in basic use but lack the internal components and software of a genuine product, to sophisticated electronics components that are not distinguishable from genuine parts by visual inspection and may not be distinguishable by basic electrical testing. The specific techniques used to produce sophisticated counterfeits vary. Remarking, taking genuine components of lower specification and remarking them with higher specification part numbers, is common and relatively simple. A chip rated for industrial temperature range, marked and sold as a chip rated for military temperature range, is physically genuine but misleadingly identified. Harvested components, genuine parts removed from scrapped electronics, cleaned, and resold as new components, pass electrical testing because they are electrically real, but their remaining service life and reliability are unknown and potentially significantly degraded. Outright fabrication, manufacturing parts from scratch to replicate the specifications of a genuine component, is the most sophisticated and potentially most dangerous form, producing components that may function in basic testing while differing in internal architecture from the genuine component in ways that affect reliability or enable backdoors. The supply chain vulnerability that allows counterfeit components to enter defense and aerospace applications is structural, rooted in the fragmentation of the procurement chain. Large defense systems integrators, the Lockheed Martins and Raytheons of the industry, typically purchase major subsystems from Tier 1 suppliers, who in turn purchase components from Tier 2 suppliers, who may source from component distributors, who may source from brokers. By the time a specific semiconductor chip reaches its position in a weapon system, it may have passed through 4 or 5 commercial entities between its point of manufacture, legitimate or otherwise, and its installation. Each transaction in this chain involves a commercial representation about the part's origin and authenticity. Each commercial representation is only as reliable as the verification performed by the party making it. The independent distribution market, the network of brokers and distributors who handle electronic components outside the manufacturer's authorized distribution channels, has historically been a critical vulnerability point. Authorized distributors purchase directly from manufacturers and can provide direct chain-of-custody documentation. Independent distributors source from a variety of secondary market channels, including excess inventory, end-of-life product, and overseas sourcing, and their ability to verify the authenticity of what they sell varies enormously. The Defense Logistics Agency, the U.S. government agency responsible for defense supply chain management, has worked to tighten requirements for component traceability and authentication, and the National Defense Authorization Acts of recent years have included provisions tightening counterfeit parts liability for defense contractors. The practical effect of these measures on a supply chain with global reach and tens of thousands of participating entities is an ongoing enforcement challenge. Beyond the defense supply chain, the counterfeit electronics problem extends to medical devices, aviation, telecommunications infrastructure, and consumer products. Any application in which electronic components are purchased through commercial channels and where the buyer has limited ability to independently verify what they have received. Medical device manufacturers have identified counterfeit integrated circuits in device supply chains. Aviation maintenance operations, which operate under stringent regulatory requirements for parts traceability, have nevertheless found counterfeit components in inspection processes. Telecommunications networks, including cellular infrastructure, have been identified as targets for the insertion of counterfeit or tampered components that could serve intelligence-gathering purposes in addition to or instead of cost-reduction motivations. The intelligence dimension is distinct from the reliability dimension, and in some ways more alarming. A counterfeit component that functions correctly but contains additional circuitry, a hardware backdoor, would not be detected by reliability testing and would not cause operational failure. It would simply do something its specification does not describe: transmitting data, responding to remote commands, or performing secondary functions invisible to the operator. Hardware backdoor attacks have been demonstrated by researchers in academic settings and have been attributed to nation-state actors in specific allegations, though publicly confirmed attributions of specific hardware backdoors in deployed infrastructure are rare. The detection of counterfeit electronics has generated its own technology sector. X-ray imaging can reveal internal architecture inconsistencies. Scanning electron microscopy can identify material composition anomalies. Electrical testing to the full specification range, including temperature extremes, voltage limits, and timing parameters, can surface components that pass nominal testing while failing at boundary conditions. DNA marking, embedding synthetic DNA sequences in component coatings that can be detected by testing, allows manufacturers to authenticate genuine components. None of these techniques are applied routinely to all components in any supply chain. The cost and time requirements of comprehensive authentication are incompatible with the speed of commercial electronics procurement. Authentication is applied selectively to high-risk parts, high-value applications, and random sample inspection protocols that provide statistical rather than comprehensive coverage. The economics of the counterfeit electronics problem reflect a familiar dynamic. The cost of authentication falls on legitimate buyers. The cost of detection and remediation falls on the eventual user, and the profits accrue to manufacturers in jurisdictions where enforcement is limited. The supply chain is long enough and fragmented enough that accountability is distributed across multiple parties, none of whom bears the full cost of a failure that may not manifest until years after the component was installed.